Morning. Yes, my name is Arnaud Gotlieb and I come from Norway. And of course, you know where Norway is located. And perhaps you, for one of them might be of the fjords, where you have fantastic landscapes, where the sea meets the mountains. You probably also love Norway because of the quality of the snow and the ski slopes. You perhaps also love Norway, the beauty of the Northern Lights. But it may happen that you don't know actually that Norway has been a pioneer in the exploitation of oil and gas in deep waters. Norway has been also a pioneer in the construction of those control chambers for the maritime industry. And Norway is also very famous for the quality of its data center application systems. And all of those actually are driven by control systems, embedded control systems. And one of the issues that we have when we develop those control systems is to ensure that they are of sufficient quality, and we have strong validation and verification processes for validating those systems. That's why in October 2011, it was decided to establish a center called Certus and dedicated to software validation and verification. And this center actually is hosted by Simula. I'm heading the center. And Simula is the research partner of the center, and it has currently 6 user partners with which we research activities. One of the partners is Cisco System, Norway, and this is this company which used to be called Tandberg some times ago, which has been booked by... Okay, I apologize for that. So yes, we have 6 user partners in the center, and one of them is Cisco System, as I said. We have another user partner, which is ABB Robotics. It's this business unit from ABB, developing those painting systems which are used in the automotive industry. We also have Kongsberg Maritime, which is this very large company in Norway developing those control chambers that I mentioned for the maritime and offshore industry. We have the Toll Custom department of Norway, which is this division of the tax department, which processes all the custom declarations coming in and out from Norway. And we also have Esito, which is an SME of the Akershus region, which is the region around Oslo. And this is a company developing a model-based engineering environment tool. And recently, we also welcomed a new partner in the consortium, which is the Cancer Registry of Norway. And this Cancer Registry of Norway actually processes all the data related to cancer to the patients and also the population of Norway. Anyway, this is in this context that we have been looking at 2 very specific industrial applications, and where we have been using some constraint programming techniques for attacking some software testing problems. First of all, we were approached by Cisco with this problem of validating video conferencing systems. Those video conferencing systems, you have probably already used them. So those are the boxes that we use for establishing calls with the distant partners, to share presentations, to share also comments. And there is quite a large product line of those products. Each of those products is a highly configurable product. So it means that it can be configured in many different ways. And the validation of those systems is quite problematic. That is because actually each of those systems needs to be validated, but it is impossible to validate all the configurations of those systems. So we have to select the configurations to be tested. So the validation of those systems comes is organized into a continuous integration process based on a quite large repository of test cases, something like 5,000 test cases and 400 distinct features. And because it runs in a continuous integration, there are in between 4 and 5 cycles a day, which select test cases, which select actually 70 test cases among those 5,000 test cases. We have been working with Cisco on different problems related to the validation of those systems. One of the first problem that we have approached with them is the test case selection problem, how to select automatically test cases for a specific cycle in the continuous integration process. Another problem has been how to reduce the test suite, how to select a test suite which preserves some properties. And I will come back on this problem later on in my talk. How to prioritize the test suite, how to select test cases in a selected order in such that we can minimize the time to give the feedback to the developer. And more recently, we've been working on scheduling the execution of test cases. It means that if we want to execute several so there is a quite large repository of test cases, and currently they have 25 distinct robots that they are using for testing. And yeah, per day there are 10 to 30 check-in changes over the code, which would require in a continuous integration process to launch a set of test cases to be executed. There is a large ongoing global project to automate the build and the test of the control systems for those robots, and we are part of this. But this is something which goes this is something which takes time to switch from traditional development to continuous integration. Requires actually some activities to be performed, and we are helping actually ABB in 4 directions. We are helping them to generate automatically test cases. So it means that based on the specific changes within the code, or based on a specific model of the timing aspects of the control systems for the robots, we want to generate automatically test cases so that they can use those test cases to test those specific timing aspects. We have also been working on test suite reduction, how to, among those 10,000 test cases, how to select a subset of test cases such that some properties are verified, respected, and also test case prioritization, test execution scheduling. Anyway, in the Certus Centre, we have developed an expertise in constraint-based test suite optimization. It means that we aim at finding cost-efficient methods for test suite optimization. By test suite optimization, I mean reduction, prioritization, scheduling. And the goal also for us is to foster the industrial adoption of the proposed method and the proposed prototype tools that we develop. We have been exploring the potential of some artificial intelligence techniques for that. One of them is constraint programming, the other one is machine learning. And today I'm going to talk about constraint programming and what we did in that area for the specific problem of test suite reduction. I just want to mention that this is actually a constraint optimization problem. We have some constraint to respect, which is the coverage of the test requirements, the coverage of the features for a specific product, for a specific control system. And we have also this optimization thing where we want to reduce something, we want to optimize a cost function. In my talk of today, I will give you a gentle, brief introduction to constraint programming, and I will switch to multi-objective test suite reduction, where we have several cost functions that needs to be optimized. And then I will speak briefly about the industrial application. So what is this test suite reduction problem? What is the core problem for that? So actually, we can formalize this problem as follows. We have a set of features. By features, we mean user requirements. We mean coverage requirements. We mean just features of a specific configuration of a product. We have a set of test cases. And we have a relation between features and test cases, which just says that, for example, here, this test case covers this feature. This test case covers this feature and this feature, and so on. So this is a relation that is given by the developer, by the tester, the validation engineers. They just tag actually the test cases so that we know what are the features which are covered by a specific test case. And the goal is actually to find an optimally reduced test suite, a test suite which is as small as possible, but which still cover all the requirements, all the features. So for example, here, if we select test case 2, test case 3, you can see that the 3 features are still covered in this process. So this is a combinatorial optimization problem. And actually, it is very well known that this is a very difficult problem to solve. It's an NP-hard problem, as we say. So what are the existing methods, existing approach to deal with this problem? One of them, very well known, it's an exact method based on integer linear programming. And actually, the idea is quite simple. The idea is to build a linear program which will optimize the number of test cases to be selected, still satisfying the coverage of the features of the system. So for each test case, we introduce a Boolean variable. This Boolean variable just is true whenever we select the test case. It is false when we do not select the test case in the final set, in the final optimized set. For each feature, we have a linear constraint. So this is for feature 1, which just says that we should at least select one of those test cases, 1, 2, or 6, because at least one of them must be included in the final set in order to cover the first feature. So we will do that for each features that we have. And then at the end, we just have to minimize, for example, the sum of the Boolean variables, which corresponds to the selection of test cases. So this is a very simple model that can be used, that have been used for solving the problem. It's an exact approach. It will give you the truly global minimum of test cases for satisfying all the requirements, for covering all the requirements. There is a completely different approach. So this is a quite good approach, of course, very powerful, but at the same time, very costly. It means that it is not so evident to, for example, put those kind of methods within a continuous integration process, because we do not exactly masterize the time that it requires to solve this linear program. There are other approaches, and especially approximation algorithms. It means that instead of going for the truly minimum, global minimum number of test cases, we will switch to something which is more approximated. Approximation methods will be used in that context. And there is a very simple algorithm that can be used for that. So we just have to select one test case which covers the most features, and then to iterate that process until all the features are covered. So it's an approximation algorithm. It will not give you for sure the truly minimum number of test cases, but it is quite efficient. And this is something that you can really integrate within a continuous integration process. One of the problems we had with this Cisco use case, industrial case study, is that they wanted to have the truly minimum, global minimum number of test cases. Why is that? That's because executing a test case in that particular context, in the context of validation of video conferencing systems, takes time. It takes the time to establish the call. It takes the time to share representation. You need to have a partner in front of you, and so on. So they really wanted to cover all the features, but really they wanted to have the truly minimum, global minimum number of test cases. So that's why we came up with another approach, which is based on constraint programming with global constraints. And I don't know if you are familiar with constraint programming, but I will just spend a couple of minutes on explaining again how constraint programming solves actually a set of constraints. So let me first mention that this is a declarative programming environment where relations are modeled with variables, domains, and constraints. And let me give you an example. So let's suppose that we have an arithmetical set of constraints. It is composed here in this very simple example of 3 constraints. We have a domain constraint, which says that we have 2 variables, x and y, which belongs to 0 to 10. We have one non-linear constraint, x times y is equal to 6. And we have finally another constraint, x plus y is equal to 5. So I'm not going to explain how it is possible to come up with such a constraint system. I just want to explain a bit how to solve such a constraint system. So solving an arithmetical set of constraints requires actually the interleaving of 3 processes in constraint programming. We have a process called domain filtering, we have a process called constraint propagation, and a process called variable labeling. And I will show you on this example how it works. So first of all, we will take an abstraction of this. So this is just a box which represents the possible values for the variable. I forgot to mention that those variables, we consider them as being integers. So in this example, we have this box which represents all the possible variables given by the domain constraints. And then in constraint programming, we will consider each constraint at a time. We will not consider all the constraints at the same time. We will switch from one constraint to another, and we will use each constraint to filter values which are not consistent with that constraint. So for example, here, if we switch to these constraints, there are some values in this box which are not consistent with that constraint. Let's examine, for example, the bounds. So if we start with the upper bound of x, then it is not possible to find a value for y which satisfies this constraint. So if x is equal to 10, you will not find any value for y as an integer to solve actually this constraint. So it means that the value 10 for x can be withdrawn. And then we can switch to the next value, and so on. Once we have done that for the upper bound, we can do that also for the lower bound. And then it means, just by looking at these constraints, by using these constraints to filter the domains of variables, we will be able to switch from this box to this box. Okay? Then there is the second process which will enter into the place, which is constraint propagation. Because we've been able to reduce something there, we can switch to the next constraint, and we can see whether it is also useful to reduce again the domain. And here again, if we take the value 6 for x, there will not be any value for y which satisfy that constraint. Okay? So it means that again, we would be in position to reduce the domain to this smaller box. Here comes something which is interesting. We've been able to prune actually the domain of these variables, and then we can go back to the initial constraint that we had and restart the process. And if we do that, we'll see that it is still possible to reduce the box just by pruning the inconsistent value of the domains. So for example, here, the value 4 for x will not be consistent with this constraint, and it will be possible to reduce the box again to this smaller box. Okay? Then we can continue and try again all the constraints. We have reached something that we call the fixed point, and this is this box, and it means that by applying each constraint at a time, it is not possible anymore to reduce the domain of those variables. Then we have to switch to something else. We have to make hypotheses in order to solve to find solutions for these constraint systems. And we can, for example, select a variable. Let's say, for example, x. We can select a value, for example, 2, and we can propagate this constraint that x is equal to 2. It's an hypothesis. If it leads to a solution, then we're fine. If it doesn't lead to a solution, we just have to backtrack and to find another hypothesis to propagate. So if we do that, yes, we would be in position to find, for example, that 2, 3 is a solution of this constraint system. It is also possible to search for solutions which optimize a cost function. So for example, here, if we want to minimize y, then it would just be necessary to add and propagate the fact that y should be strictly less than 3, because we have found a solution, 2, 3. So if we want to see if this solution optimizes a cost function, we just have to add actually the constraints that y is strictly less than 3. And in that particular example, we will find that, for example, x equal 3 and y equal 2 is a solution. Yes, it is also possible to prove optimality. Just if we adopt a way to explore or to guarantee that we have explored all the search space, it is possible to prove optimality for this cost function. It is also possible to find all the solution by this process. Constraint programming actually is routinely used in validation and verification. It handles hundreds of thousands of constraints and variables without much problems. It is something which is versatile. It means that it is possible to tune it, to program it. So, for example, we can define our own user-defined constraints, our own constraints for solving a specific problem. There are dedicated solvers that can be also tuned. It is possible to program search heuristics. You know, those search heuristics are those selection of variables, selection of value thing that I just showed you. But of course, at the same time, it's not a silver bullet, because developing efficient CP models requires expertise. There is something that has been developed in the CP, in the constraint programming area, which is this notion of global constraints. And a global constraint is just a relation over a non-fixed number of variables, which implements a dedicated filtering algorithm. It means that it is possible to either reuse existing global constraints that have been proposed by a researcher in that area. It is also possible to develop its own constraint with its own processes to filter the domains. And I have a first example to show. So this is the nvalue global constraint. It's a relation between a variable, n, and a vector of variables. And these constraints just constrain the number of distinct values that this list of variables can take. So instead of going through this definition, a bit formal for today, I will just show you a couple of examples. So, for example, if we just look at this example here, the number of distinct values that can arise here, actually, is just 2. So it means that if we set up this constraint, we will get the answer that n is equal to 2. Another example is if we just enforce the fact that there are 3 distinct values in a list of 2 variables, then the constraint will just fail. There is nothing that can satisfy these constraints. Equally, if we enforce the fact that there is only a single value in a list of 3 variables, then we will enforce equality between those 3 variables. So now it's time to come back to this test suite reduction problem. How to use this to solve the test suite reduction problem. So remember, with this example, we wanted to find an optimally reduced test suite which cover all the features for this example. So first of all, it is possible to create a variable for each of the features. And we can give as a domain the test cases which covers actually these features. So for example here, F1, we know because we have access to this relation here. We know that F1 can be covered either by test case 1, by test case 2, or by test case 6. So we can just actually consider that F1 is a variable and it has domain 1, 2, 6. And if we find a solution, we will actually find an assignment of F1 to one of those values, saying that this feature is covered by this test case that has been selected into the set of test cases to be included into the final set of test cases. And then it is possible to set up this constraint nvalue, which says that we will create a variable called max nvalue in that case, which will actually just be constrained to be the number of distinct value taken by this list of features. If we now minimize this value, we would be in position to solve the optimal test suite reduction problem. We would be in position to find actually that this set of test cases covers all the features in this example. So this is an example where it is possible to use simple constraint programming tools to solve a test suite reduction problem, a software testing problem. One thing though, here the variable of this model, this is a constraint model, and the variable of these models are variables associated with the features. But it is well known for a very long time now that it is also very interesting to have access to variables which correspond to test cases. So we would like also to be in position to, for example, select a test case which covers the most features. And that's all. Yeah, this is a reason why it might be also interesting to look at other models to solve this problem. So another model that can be designed for this problem, yes, only F1, F2, F3 are available for this labeling process that I mentioned to you earlier on. So another constraint that have been proposed in the CP community is the global cardinality constraint. It's a global constraint, and it has a quite formal definition, but the general idea is just to constrain the number of times a specific value is taken by a list of variables. And I'm not going through the definition, I just want to show you an example. Yes, there is the interest of using such a constraint is that it comes with a filtering algorithm, a dedicated filtering algorithms, which is based on advanced techniques, such as, for example, computations of max flow into a network flows. But I'm going to switch to the example. We can encode this problem again with these GCC constraints just by using the following. So if we set up if we still have variables associated to the features, we can create variables associated to the test cases. And by using this GCC constraint, it is possible actually to encode this relation. We will say in that example that test case 1 covers exactly V1, which is this variable here, features in this list, okay? So the syntax is a bit weird, but actually it's very simple to understand. We have, for each test case, a variable which will be used to describe the number of times a test case will be selected to cover a specific features. So if we just set up these constraints, we will get the following result. And it is possible to find a feasible solution, so a solution of the problem, just if a solution which satisfies this constraint, which is also something which satisfies actually the fact that we have covered all the three features. So if we select test case 1, test case 2, test case 3, and none of the others, it's a feasible solution in the sense that all the features actually will be covered. But as you can imagine, it's not an optimal solution. So if we want to get an optimal solution, we need to do something else. And the first idea that comes into the mind is to use the exactly same constraints for doing that. So for solving the optimal test reproduction problem with GCC, it is possible to use another GCC constraint. So just how to do that? Just by maximizing the number of times we will not select specific test cases. If we maximize the non-selection of test cases in the list of test cases to be included in the solution, then we will have an optimal test suite reduction for this problem. So I will not go through all the details of this, but what has been observed is that unfortunately filtering domains with GCC is quite costly. Actually, it's a cubic algorithm which is used, and this is also something that needs to be kept in mind when programming with constraints, the complexity of the filtering algorithms which are used in the global constraints that are used for that. I just want to mention that there is a catalog of all the global constraints available, which contains more than 300 different global constraints. And then comes into mind the idea of mixing those two models, mixing the models using the GCC constraints and the model using the nvalue constraints. And that's a model that we proposed, which is called mixed. And actually, it just replaced the second global constraints, the second GCC constraints by these nvalue constraints. And by mixing those two global constraints, it is possible to come up also with a model which solves the optimal test suite reduction problem. I just want to show you a couple of results for that. So this is the comparison of those three models. So here you have the model which uses only nvalue, the model which uses a combination, the two GCC constraints, and this is the model which mix those two global constraints. And we are just comparing here the percentage of reduction. So the smaller, the better. We want to reduce as much as possible the number of test cases in a given amount of time. Yes, I did not mention that, but this is something which is very suitable to be integrated within continuous integration, because the optimization process can be stopped at any time. It is also possible to give a contract of time to the optimization algorithm and to get the result at that time. So we just compare actually the percentage of reduction for all those three models, and we observe that in all the cases, the nvalue model was less efficient than the two others. You can see that's true for all those random instances. Yes, we generate at random some instances to compare the approaches, and you can see that the range of you can see that the range of features actually goes from 250 to 1,000, and the number of test cases ranges from 500 to 7,000, which corresponds more or less to the size of the problems we have to deal with in our industrial applications. Another thing that needed to be compared is the time that is required to get to optimize. Because if we had to integrate this into a continuous integration process, you have to really fine-grain tune the time required for optimization with respect to the time required for testing. So here we made another experiment, which was actually to let run the system for getting a truly optimal solution. And interestingly, we observed that at least in those cases, the time required for the model with 2 GCC was much more high than the time required for this mixed model. That is true for actually those three last set of experiments. So we decided then to keep this mixed model to be integrated within our tool. And we also implemented a couple of other things, other tricks to solve the problem. And we have something that is called model preprocessing. And model preprocessing is just the implementation of rules that can be used to simplify before optimization the problem. And this can be done in a quite simple way in constraint programming. So just to mention, for this particular very simple example, very toy example, it is possible to solve it just by using preprocessing rules. So I can just perhaps explain this one. Just by observing that all the test cases that covers, among the test cases which cover these requirements, so we have test case 1, test case 2, and test case 6. This one is a bit more interesting than the other. That's because this one also covers something else. So if we would have the choice between those 3 test cases, this one should be preferred because it will also cover something else than the features that we want to cover. So this is just an example of a pre-solving rule that can be implemented. There are many others. And just by implementing those rules and applying iteratively those rules, it is possible for this particular example, but to pre-solve quite significantly the model. All right. Optimizing the size of the test suite is one thing, and it's important, but it's not sufficient. There are also other things to be optimized. And of course, in real settings, we also want to optimize the execution time. We want to optimize the time that is required to execute the test suite. And let's suppose that we have from history, we know that the test cases takes some time to be executed. Then one of the goals is also to optimize the time required to execute the test case. Because if we do that, we would be able to schedule more and more and more test cases in the continuous integration process. So in this example, this is another set of test cases which can be selected in order to optimize this execution time. Execution time is one thing, but there are also other things to be optimized. For example, fault revealing capabilities. From historical data, we also know that some test cases they should have more priority than other test cases because they are able to reveal faults in a much better way or in a more interesting way. So, for example, we can tag, or we have tags for the test cases, which says that this one should have a higher priority than this one. And here again, the goal might be to select a subset of test cases which maximizes the priorities that we have. So I just mentioned two different criteria than just the number of test cases, but there are many others. You can also consider, for example, the coverage of each test case. In some settings, in some industrial settings, we know that a specific test case covers a specific piece of the code, and if we want to maximize the coverage of the code, then it might be interesting to select test cases such that this coverage is maximized. Here again, there are different approaches which have been proposed. One of them is based on something that we call actual multi-objective optimization. So it means that for each objective that we want to optimize, we will assign a weight, and we will balance using the weights the criteria to optimize. This is a quite complex setup, but it works, and there are algorithms for that. So the idea is just to aggregate actually a cost function using different weights for each objectives. Another approach that we've been working on is by using global constraints again and constraint optimization. And the difference between those two approaches is that in the first setup we have only approximate solution, while using constraint programming we are in position to have exact solution as well as approximate solutions. In this setup, we don't have any constraint model to reason with. It means that we are not able to prove any optimality result for that. While in the case of the CP model to be used, we can actually we have a constraint model to reason on and to perform reasoning, and it means that we can actually make proofs, formal proofs, on the optimality of the solution that is found. So. Yeah, excuse me. So we just proposed actually a model which is also based on global constraints. It uses another global constraint called scalar product. And just by considering that each test case could be associated to a specific cost, which aggregates the values of different criteria to optimize, it is possible to come up with a model which also solves this problem. Okay, industrial application. So this comes from research results, but of course, applying those research results into an industrial setting is always problematic, is always difficult. So what we did is to implement a solution and to validate the solution with our industrial partners, Cisco. And the solution that we propose is implemented using Sixtus Prolog, which is a Prolog development environment developed at SIX. And it is based on constraint logic programming. And we developed a tool called Titan, which is a pre-industrial tool, which reuses some components coming from another commercial tool, which is called Pure Variance. And Pure Variance is the market-leading tool for variability management, feature modeling. It is used for modeling software product lines and variability among the configurations for different products. And we developed a desktop version and a web-based service for this tool. And the tool is under deployment at Cisco System Norway. So I just included a snapshot of the tool. So you can see there that we have actually a video conferencing systems with all its features, and this can be encoded as a model, as a feature model, which actually corresponds to all of those features, corresponds to a specific feature of this system, and there are links, there are constraints between those features. We have a test suite, which is used as an input here, which represent actually, which gather all the features of which shows all the features which are tested by this particular test suite, and we can see here the coverage realized by this test suite. So, for example, all of those features, they are tested, they are covered by this amount of test cases, this amount of test cases, and so on. Behind this tool, it is possible to optimize, so to extract a subset of test cases which still respect the coverage of the features. And we also have here some diagnostic views and over feature coverage, and also what are the features which have not been tested by a specific subset of test cases. Anyway, the tool has been evaluated into an industrial settings. And I will not go through the details, but I will just say a couple of things about the results. So we observed in this experimental setting that the time taken for test suite optimization is negligible with respect to the time to test the system. So that was considered as something important for integration at Cisco, because they wanted to really be in position to optimize at no cost in the continuous integration process. That's because they have 5 cycles a day for testing the systems, the control systems for the video conferencing systems. The reduction rate that we were able to show lies in between 30% and 60% of remaining test case, which was considered as interesting for them. And unfortunately, these experiments remains quite modest in size, and more experiments would be needed on industrial case studies which are of larger size, but this is an ongoing process. Okay, it's time to conclude. First of all, I think that, or at least I've tried to convince you that constraint programming with global constraints is a convenient tool to efficiently tackle this optimal test suite reduction problem in industrial settings. But of course, as you have seen, we came up with different models, different global constraints to be used, and actually it means that some expertise is required to develop those CP models. The full industrial validation of what I've shown you is engaged at Cisco, but we have just started the discussions to also use this or to explore this new industrial case study with ABB, and we just understood that some revalidation was necessary. So in particular, we need to adapt the format, we need to adapt the documentation, we need to adapt everything in order to be able to address a new case study. And that's always a problem because we need some resources for doing this, and it's not always as trivial as we thought it should be. I want also to stress the fact that other optimizations are possible. We have just tried out only a few global constraints, and we are not specialists of the development of global constraints or the usage of global constraints. And we guess that there might be other global constraints that could be useful in that context. So I think that there is room for more research and innovation in that area. And I just want to mention that if there is any interested partner that would like to try out this optimal test suite reduction thing for its own processes, its own development processes, then I think it might be useful to look for research areas, research activities on the usage of different global constraints for that purpose. Okay, thank you. That's all from my side. I just want to thank actually my co-authors. This is not the work of an individual, it's a collective work. And I want to thank Mats Carlson, who is in the room, for many different things, but also Duchitsa Marijan and Carlo Ieva and Alexandre Pétillon, who have been working with me on this particular work. Thank you very much, and I'm very welcome to take any question that you may have.
Questions? Anybody?
Yes? I'm perhaps not the greatest specialist to be in position to respond to that question. I can perhaps just respond on the test suite reduction problem. So yes, if we increase the number of test cases, if we increase the number of requirements, then the optimization problem tends to be more and more difficult to solve. So, and that's probably, most probably because it's an NP-hard problem, so it means that we have a combinatorial explosion at some point. Whether we have much more precise results on how to understand how the complexity grows with the size of the problem is something perhaps for the specialists. And I know that there are specialists in the room, so I don't know if you have something to say, perhaps about constraint programming and the size of the problems.
I mean, this is quite interesting because it is actually a property of these problems and not a property of these methods. So it is inherent in the structure of these problems that no matter what method you're going to use, you know, it will be difficult, right? So this is this NP hardness problem. And what that typically means in practice, yes, there will always be a point beyond which you will not scale, right? This is clear, and all these techniques are actually meant, like constraint programming or any other technique, is to push the envelope for that point as much as you can, right? So this is the idea, but yeah, you know, eventually it will break. But this is really a property of the problem, not the method.
And we don't know where.
No, and we don't know when. And you know, what we try to do is always to push that point as far as we can. And actually, we have been quite good in the last 3-4 decades to get the point to a place where nobody ever had believed it would be possible to push to that point. Right. Leif?
So did I understand it correctly that each test case must be tagged which feature it covers?
Yes, absolutely.
So if you have 20,000 test cases, there's quite a lot of work tagging and keeping that tagging up to date.
Yes, it's the work that is performed by validation engineers. So it means that they have to actually set up a purpose for the test cases that they invent. So of course, we are talking here of systems which have been developed for more than 20 years. So these didn't come, you know, like that. So it took a long time to come up with such a framework. I just want to mention that we have also discussed with some industrial partners where they don't have this one-to-one relation. So usually they consider that a specific test case can cover partially a specific feature, or that actually several test cases need to be used for testing a specific features. We haven't really worked on this, but I think that the framework could be adapted. I think it's not too difficult to adapt the framework to such an environment, but we haven't done it yet.
So please take the opportunity in the coffee break to ask more questions or have a chat with Arnaud. So let's thank Arnaud again. Thank you very much.